start the recording and we'll get started. So yeah, the first thing I want to talk about to end up with this final result is a bit of noise functions and stuff like that that are being used so that over time this stuff will get a random path that it kind of walks through, or it's just being influenced by kind of like a wind force or something like that. Previously we have used the random function. So if we go back into this new file, let's just do our classic UV. We'll just do the U parameter, or the U variable from the Y position, or the height. And then that's just storing the coordinate. And we're doing this is just our classic like graphing calculator way to visualize functions or waveforms or stuff like that. So we set the X position to U, and then we just have like Y equals X here. So over time, U is kind of time, or X is time now, and then Y is the output. So if we do P dot Y equals random of U, this is the random results, or it's pure incoherent kind of noise. If you know, or you like did stuff with synthesizers, this is like static, or it's like white noise. It's just incoherent. Or if you really watch like old TV channels or stuff like that where there's static on the broadcast, that's kind of what this is just pure incoherent white noise or pure randomness. So with the idea with these like more improved noise functions is that they have a bit of organic patterns to them. There's like an overall kind of cohesiveness to it. So it's not just each step is purely random, if that makes sense. So this will just be random. And if we keep going with this, you could take a look at, let's, if we just do floor of U, then you can see like the individual step. So basically from 0 to 1, this is all just a single value now, if that makes sense. And if you want to extend it or increase the frequency, like with the sine function, we were getting one peak and one valley with one unit of frequency. So you could say float frequency equals 1. And then we'll multiply U by this frequency. So it didn't change anything, just multiplying it by 1 is unchanged. But if we increase this to 4, then we get 4 different random results or waves or whatever through this function. If you add, somewhere you could do this is add time to it. Just do it at you want to probably do it after you've scaled the frequency. So we'll say U plus equals time. So now we have our little kind of oscilloscope or waveform generator or whatever, like scrolling over time. So again, this is still pure random. Like each of these steps right here is like kind of rolling a new dice or flipping another coin. This is more similar to a dice because these results can be like anywhere between 0 and 1. But you get the idea. So let's just blast away. We could keep some of this stuff, I guess. So what was invented, or an improvement to noise, not necessarily to always use it, but can be useful, is this Perlin noise or noise. This is a function here, and it's just computing, you can see more of a cohesive signal. It's a little bit more predictable, but it's like not pure random, if that makes sense. There's times and places to use each one, like sometimes you want purely random, but sometimes for a more organic feeling, you want a bit of cohesiveness to your random values or your noise function. So we could keep playing around with some of this stuff. You get the idea here. And a good reference is, let me see, I think I have it in this file. So we have some side effects documentation for, let me get a new window here, for noises. So this is the one that I'm using. You can see, depending on the inputs and outputs and stuff like that, you can generate different results. So right now, this is using it to just generate a one-dimensional result. It's basically just going up and down. If you do a grid, you can just increase the density of the grid and keep going with a wrangle. We'll say P plus equals or add noise. And then this, I'm going to generate the noise based off of the current position. So you can see when I do that, we're getting random like 3D displacement or 3D results of the noise. If we multiply it by a bigger number, this might actually be, it looks like this is just going in one direction. So you have to specify sometimes with these noise functions. It might have been when I multiplied it by 5, it thought that I just wanted it to be a scalar or like a single result. So sometimes you need to specify and kind of manually tell it. Multiply the P. Yeah, you can do that. So this is the amplitude that I'm changing at the end. And then if you want to multiply or adjust the frequency, you could multiply the P. So these are two different kind of parameters. Frequency, similar to sine waves and stuff like that we were doing, is just how much the repetition is happening. And then this is just how much you're scaling the end result. And another thing you kind of have to be careful of with these noise functions is the range of the results. Like they aren't always generating random numbers in the same space. You can see this one says the noise is in the range of 0 to 1 with a median of 0.5. So it's kind of like that random function. Sometimes when I was using it, what I would do was subtract 0.5 from the result. So if you do minus 0.5, then you just kind of recenter it back to the origin, or it's like 0 centered instead of centered at 0.5, if that makes sense. So again, with this, you just get a little bit more organic kind of feeling and stuff like that. There's other noise functions. I'm not going to go through them all today, but we'll just look at a few more before we move forward. So there's this curl noise. There's just this standard noise. There's the S noise. It's like simplex noise, I believe. You could look all these up if you think just down here you see there's a lot of other ones. So this saying, I don't know if they name it here, but I believe that this is simplex noise. There's this This X noise, I believe, is actually simplex noise. I'm not sure what the S noise is. But yeah, this one is simplex noise. Hello, Alex. Yes, this is the crumpled paper generator, wavy paper. And then, so we did regular noise, S noise, X noise. There's O noise, that's like original Perlin noise. You could see as I'm scaling these, that's like moving around a little bit. O noise is kind of a special one that is centered. You could see here, it's the bounds of the noise are between -1 and 1. So this one's already like centered at 0. So it's just a bit of kind of like precautions you need to take when you're generating your noises and stuff like that. This is like a Vex workshop today, Alex. So I'm generating these like plants or whatever using Vex. We've been building up to this just through previous weeks every Sunday, using Vex and just trying to see what we can create without using trying to use as little other parts of Houdini as possible, just to kind of like challenge ourselves and improve like scripting, coding capabilities and all of that stuff. So if you go to, looks crazy. Yeah, it's there's been a few others of these, but yeah, each one is like a little demonstration. So this is growth we did earlier. In the earlier weeks, it was kind of like morphing between positions, rolling, like rotations. We did bouncing was the first week. I don't remember them all. If you go to the YouTube channel, there is a playlist for them that's just all the Vex Express. So then if we just keep moving on with these noises, we have curl noise and curl X noise. So if you want to experiment yourself, you could play around with some of these. Let's just go maybe with a lower frequency and just try them out. But you could hopefully see just by going through them like a bit of how they vary or how they're different. But overall, it's like this very low frequency kind of smooth deformation. Does the fourth component in an input of the 4D noise work? It depends on the noise. Again, you can look up here and like certain of these, the O noise, for example, there is no fourth component support, I believe. With these curl noises, I believe you can do it. So you can see right here, they're saying you can do a vector 4 input. So it depends on the noise function, whether it will support it or not. If you want to try it, you could do, sometimes I'll do like vector 4 noise position. You would set it equal to P. So this is putting your position into this vector 4. And then if you want to update noise pose, it would be .w for XYZ W for like four components. You would set that equal to time. And then instead of specifying P right here, if you use noise pose, I'm just calling it that because it's like the input noise position. So then you would see here, this is updating over time. But certain ones, you might find it will like yell at you. Like here, it's saying it can't expect a vector 4. This function won't be able to interpret, or it just can't read the fourth component. So it depends on the noise function for vector 4, or four-dimensional noises. All right. So let's just go back to X noise. So that's pretty cool. Just some somewhat coherent randomness. And another thing is that some of these noise functions will take, they can generate like what's called FBM noise. Believe that stands for like fractal Brownian you see, fractal Brownian motion. This is layering several octaves or several levels of those noise to give you a more complex result. So you could see with these noises I've been generating, they all look pretty much the same. So someone built on that. This is like a very old, in the 80s or whatever, someone built on that technique of just these simple noises, and they combine them using like a fractal method. And if we go into some of these Vex noise, not this one, but the O noise, you can see this one will accept the turbulence and roughness parameters that allow you to generate more complex noises. So if we go into this O noise, then you can add extra arguments that would be the number of octaves, the roughness, and then the attenuation. I usually just leave the attenuation at 1 all the time. And I think, again, this one I was saying earlier, we don't need to center it at 0, because the results are always between -1 and 1 for O noise. Let's maybe go with a lower frequency for the position. So you can see now I'm getting a little bit more detail, like multiple levels of detail. So that's just the difference between a typical noise function. So a lot of those noise functions are just like 1 octave of noise. They don't have the extra layers that you're used to seeing if you've used noise in VOPs and stuff like that. So this is the number of octaves or the levels of noise. This is the roughness. And the last one is attenuation. So this is FBM O noise. And if you're curious about how FBM noise is constructed, this is an example of how it's constructed from scratch. And could do a dump of the file. Let me update you guys so you aren't stuck looking at a compressed stream to get the code. So this is an example of how you could construct, or how the FBM noise is constructed from scratch. So like I was saying, this noise function, just standard noise, doesn't allow you to do multiple arguments to generate like multiple octaves. So this O noise kind of under the hood, or internally what it's doing when you specify multiple octaves and stuff is working like this. So as you're adding these multiple layers, you can see it's just putting in smaller and smaller detail. So if we do maybe less roughness, then you can see it's just each extra iteration is giving you like less and less impact on the final result. So it's basically keeps repeating itself and calling the noise function, but each time scaling the frequency, reducing the amplitude to give you this like extra detailed kind of look of things. So hopefully that makes sense, getting people familiar with noise. We'll start to go into building this kind of form now that hopefully people are familiar with what's going on, or how noise is different from the other functions we've been using. So we were using a lot of sine waves and a lot of randomness before, but now to give you like, you could use sine, but here for if you were doing maybe like a fantasy kind of vine where you wanted everything to be very curvy and very neat, like each of these would be more circular or something like that. But if you want a more organic, unpredictable kind of result, the noise functions are pretty valuable for that, or just adding some subtle variation to everything. All right, so this is our little noise exploration. So we did randomness, we kind of did this kind of quantized randomness, or just to examine more closely the results, and then noise to get this more unpredictable balance of like, it's like an in-between kind of sine and purely random, I would say. Just as in terms of the result, like artistically, if you're thinking about using it. So now we'll talk about adding primitives and vertices using Vex. Anyone feel free to jump in if something isn't clear or something doesn't make sense. So I'm just going to start with this point generate again. Go into the point markers. Just make it bigger. Did it happen? Maybe this needs to be. I think the point marker size is actually like this little dot or whatever. So I usually will use this as just a way of, I think I've used it before. When we were making bouncing balls and stuff like that, this was just determining how many points we're going to start with. So this is just a good way to give your wrangle like an input, and then it will just run this code over however many points you specify. And then previously what we did like in Vex was add points, but in this case I want to build a line or create curves from this source point. The way that you do that is with these two functions here that I've put in. Basically, you need to tell it the line that you're creating, and then you need to use vertices to attach the points to the line. So it's kind of just the way that geometry is constructed in Houdini. You use vertices to tell when points are belonging to primitives, essentially. I think Matt Estella did a really good job explaining it on CG Wiki, talking about like prim vertices and points in Houdini. He had this example of using like sails or like a tent. The vertices are kind of like the hooks that are connecting or assigning things to which thing that they belong to. So point is defining like the 3D position, and then vertex is whether it's like connected or attached or belongs to it or not. I don't know if that helps you guys, but it's a pretty good, helped me kind of conceptualize things a little bit. So what we do here is we can make a line like this, and then you do the add prim function. Got all kinds of spelling errors today. So we do add prim and polyline, yep. So we do 0 here. This, you could do geoself, or 0 is basically you're just saying the primitive is going to be added to the current geometry or to itself. And then you can specify the type of primitive you want to be adding. So in this case, it's going to be a polyline. There's other things you would want to do, like faces, NURBS, packed primitives, like you can get into, there's all kinds of other business and stuff like that. You could even do sphere, like those other primitives of tubes, kind of the geometric ones, metaballs, alembics, all kinds of stuff. So we added the primitive. If we go into our spreadsheet, you can see that it exists. Like before this, there's no primitives. It's adding a primitive, but you can't see it. Basically, there's no geometry, there's no lines that belong to it. So visually, it just doesn't show up at all in the viewport. So we want to add points to it. You would need to start making vertices to attach points and stuff to it. So we can do the add vertex command function. And again, you want to do 0 to say we're adding the vertex to the current geometry. If you go over here in the vertex tab, you can see it's empty right now. We'll do add vertex. And then the next argument is the primitive or the polygon or the line that you want it to belong to. So we're saying add the vertex to belonging to this primitive. And then the last one is the point that you want to add, or the vertex that you want to be. Basically, like you're using this vertex to connect or to parent a point to a line or to a primitive, if that makes sense. So we could do pt num to basically connect it. So we have our point. This vertex is basically saying that the point is belonging to this primitive, and we've done it. We can't see anything because this line doesn't have any length, or it's just basically only one point. It doesn't have a start and end point. It just has a start point. So if we want to make an end point, we're going to need to add another point to the geometry. You can do add point, 0, again for myself, and then the second argument for the add point position, for the add point function, is the position that you want to add the point at. So if we do set, we'll just say like 0, 1, 0, and that's it. So we should see, I don't know why these, might be because they're, because of the primitive. Let me try this for a second. Sometimes, all right, there it is. Sometimes when you have points that don't belong to primitives, or you're messing with that stuff, it doesn't always show up. So like this point, because the first one I assigned it to the primitive or the line doesn't have any length, so you just can't see it yet. So if we want to add this point now and say that it also belongs to this line, we could go ahead and just do another add vertex. This is going to be our, you would store the point number that you're creating using this pt variable. And then if we do a second add vertex command, instead of the current pt num, or the one that's being fed in here, this one can just be pt. You would call this like end point, like that. If you want to be really fancy, you don't want to do as much typing, you can do a special kind of function, or just set this up in a kind of fancier way. So do it like this, and it will still work. So what's happening here is we're adding the point and returning the resulting point number inside of this function. So it depends on your coding style and stuff like that. It's a bit more complex to think about, but it's like a little bit cleaner to type out as one line of code, if that makes sense. So either way, we're generating a single line, and then just connecting, or starting with setting up start and end points. So that's our line. If you want to get fancier and generate like more segments to your line, you can do that using loops, or the for loop we've used before. So you see here that we just have start and end point, but the line doesn't have any internal like segments or anything like that. So it's good to go ahead and do that now. And let's just do for, so you have the integer that's going to be your kind of counter for the loop. And then you have the condition of like how long the loop should be running for. So we'll say maybe we want 10 segments, and then the increment. So pretty much always people will just do plus plus to just step up by one number, or increment by one. And then you use the Egyptian, the curly brackets, to start and end the loop. All right. So I did something wrong here. There's some green underlines. I forgot to define I like as it starts. So we just want to initialize it to 0. So it's just complaining that this was an uninitialized variable. I think internally will automatically be initialized to 0, but it's just a little bit dangerous to rely on the program to handle that for you. Usually people want to define it themselves. And then you could see right now all of these endpoints are all getting set to 0, 1, 0. So it doesn't, visually our line doesn't look any different. If we want to improve that or fix it, we can just divide, let's do maybe 1 divided, let's do I times 0.1. And we're in pretty good shape, but just the start of it, because we're initializing I to 0, you would see it's still, the first point is overlapping with this 0th point here. So if you want to fix that, there's a bunch of different ways to do it, but maybe you would want to do like I plus 1 times 10. So now we have our kind of connect the dots line happening. So this, we'll just say multi-segment. If you guys are following along, you could do another update. Just so I know it's a bit of a pain trying to follow along and retype stuff in the window as we move along. So that's pretty cool. But we want to start adding some noise or randomness or stuff like that to the point position. So let's just keep going with that. So what we can do here, let's make another variable. And this will be the current position. So what I'm going to do is copy the point position, into this variable. So we can update it over time if we want. And instead of this, updating it like that, what I can do is use the pose position variable. And then it looks like, what have I done? It's just an extra bracket or extra parenthesis left over from that set function. Okay. So we're back at the origin. We're back at the starting point. We're back at the beginning here. We're not moving the points at all or anything like that. So if we want to do something a little bit fancy, what we can do is each iteration of this loop, we can add some value to the position. So if we do, historically what we were always using was the random function. So we just add a random number to the position. Could generate a random value based off of the loop counter. Then you can see we're getting this kind of like jagged line. This random function is giving us a random number between 0 and 1, and then it's being cast or translated to a vector. So that's why it's going diagonal in each of the axis, x, y, and z. It's traveling positive in all of those directions. So if you wanted this to be purely random vector, this is another situation where you want to make sure you're telling it to use a vector. And then another thing you're going to want to do is subtract 0.5 at the end if you want it to be centered at the origin or centered at 0. So now we're just drawing a line. Each segment of the line is getting moved to a random position or incremented to a random value. You could play around with this loop and really crank it, and get some big numbers, get some big values like that. And of course, playing around with the point generate, you can add more points. You don't see any visual difference here because this random function is giving you the same result for each point. So we have a bunch of lines, but they're all exactly the same. So if you want to differentiate them a little bit, you could add the PT num. So basically, I is unique to each step of this function or each iteration of the loop, and then PT num will be unique to each source point number. And then if you just want, like right now, everything's looking pretty close to the same. Sometimes what I'll do is like another random number from the PT num and just multiply that with like 1,000 or something. So then you just like spread out the random numbers from that PT num. Otherwise, if they're all between 0 and 1, they're very similar. So this just makes sure that they're very unique random numbers there. So we do, just go back to 1, and you could just add more if you want to. So I think similar to the FBM noise, this is another thing that's just, I believe, called Brownian motion. What we're doing here is very similar to this. And I think this techniques, or one of like the inspirations from this came from a scientist or a mathematician observing like a particle of dust or a bubble or something like that on top of a liquid or on top of his coffee or something. So the idea is that over time there's wind or just subtle forces or things like that shift things around in a purely random, like non-deterministic fashion. So that's the difference, or another difference between random and noise, is like each iteration is just purely random. So if you think of something floating on a surface, you could approximate it kind of like this, where it's just each the position in time is just randomly getting moved around. It's like a random walk is another name for it. And if we want to just call this Brownian motion. And then if we want to add or animate this, instead of manually putting numbers in here, if you just did like frame, then over time you can visualize the movement or the growth of the line. So we could do another update. And if we want to implement or get away from this purely random result, we could implement our noise functions that we were talking about earlier. So instead of this being a random number or just a purely random result being generated, let's just get rid of all of this. And we could do curl X noise. And you generate it based off of the position. And then you'd like divide the position maybe by, let's try it divided by 10. This is like a lower frequency. So as you divide the position, you're just adjusting like the swirl size. Lower frequency is bigger swirls or bigger features. And then if you multiply it, then this is like a super high frequency that even the points are not encapsulating like all of the curves and everything of it. You could also multiply by a small number instead of dividing by a big number. It's the same thing. So now, instead of the Brownian motion, we more have like a, this could just be like a growth motion, or it's like there's a bit of wind, or it's more of like a bird or something like that that could be flying through stuff, if that makes sense. So instead of walking through purely random, like chaotic collision thing with the noise, with the random function, we're using noise to walk through like a flow pattern or something that has more of a organic or underlying motion to it. And if you guys are familiar with it, or you've probably seen this before, if we do a grid, we'll just do a bit more frequencies. And you just set this to generate a grid of points. So no polygons, they're not attached. It's just points. And if we plug our input here, this is very similar to like the trail or volume growth, or those kind of like curl noise renders, or whatever you want to call them, the flow lines or whatever that people are fond of making. So this is the same idea. If we extend this out with a grid, you play around with this and get some interesting stuff. So it's the same idea as just the points walking through noise space or getting pushed around by noise over time. So this is a situation where noise is very useful, or noise adds a bit of organic structure to things. If we look at the same process, but just use our Brownian motion or the random walk, you can see that these all have no relation to each other. They're all doing their own like independent thing. So it's just not as interesting as like an end result. It's just kind of pure chaos. So that's why the noises get used, is just to add a bit of controllable kind of structure or motion to things. So that's pretty cool. If you want to get up to date, we could do another publish of the file. And of course, you could play around with the different noises. You can see like the X noise. I was saying this one, certain ones you have to be careful, they aren't centered at 0. So that's why this is traveling in a specific direction. But yeah, you can plug in our other noise functions and see what happens with the different results. All right, so we want to keep moving on. Spaghetti code is like a procedural node, just making a bunch of node wires spilling out all over the place. All right, so we'll keep moving, and if we look at this one, or the final result or our goal, you can see that there's some branching and splitting and stuff like that that's happening. So that's going to be the next thing that we'll look at adding or building in with this. And what we can do, let's just keep this here. I'm just going to go back to, let's just keep going down. I'll grab this one. So we're back to just one point, one source point, and one line. It's just a little bit easier to visualize things this way. So what we can do is just keep writing more code to branch off or draw more lines. So here we have the line prim. What we could call this is maybe, to be a little bit more clear, this would be like the main line. I'm just going to update the other places where that gets used. What have we done? Didn't like something? Maybe it doesn't like my name. Maybe I don't know, maybe the clipboard got messed up. I've been having some weird issues with like this copy and paste of code in 18.5. We'll keep moving. So we have this line right here. Yeah, I don't know, maybe it's a weird, there's like a ASCII or Unicode symbol, or it was a weird thing with the clipboard. But we're back in business. So let's try to get some branches going off of this thing. What we can do is just keep going down here and making another primitive. And this one, we'll just call this maybe a branch line. We have to be a bit careful because we're doing kind of like a recursive thing, or like this is going to be, the growth is not linear. Like each iteration here, this is going to be creating a branch, and then if we add more curves to that, like it's going to be a you can easily like get out of control with it. So we have the branch prim that we created, and then if we make another vector, this is going to be the branch B branch, the branch position, and we can just put that as a copy of the current position, and then we can go in and start making our branches. So let's do another for loop. Sometimes with these for loops, when people are nesting them or just coming up with new integers, they'll do like ijk. They usually do that for 3D like voxels if you have like XYZ, IJK or whatever, but I'm just going to keep going with that convention. So this J is going to be our branch counter. And then this is going to be how many segments we want the branch to be made up of. And then again, just do J plus plus for the increment. And then we'll open and close the brackets. And before we start branching, we'll just want to add like the base connection or the base point before it splits off. So we'll take our branch pose, and I think I actually want to do something more like this one. All right, so we're going to want to add this to the branch line prim instead of the main one, and we want to add the point at the branch position. And then in this loop here, we can just start doing our same motion and adding. So we basically, each iteration of this, we're going to move a little bit and then attach it, and then move a little bit and attach it. Just keep repeating that over and over again. So we could, let me just type this out. So we'll take our branch position, we'll increment it, or just plus equals is saying take itself and add, kind of move it a little bit in this case. But plus equals is just add the result to itself. So we'll keep going with the curl x noise. And we want to use the branch position as our noise coordinate system. We want this to be a lower frequency. And should be good with that. And then we just want to add the vertex to this itself, the branch line prim. And then we need to add the point. And then the position. Aha! So we have something happening. It's not super close to what we want, but it's in the right direction. So one of the issues is that every step we're adding a branch. Another issue is just that these branches are too similar. So it looks a little bit odd, or it's just not what we're after. So what we can do is, instead of using the same branch position for each of these, if we add a random number to it, in this case, we probably want to use I, so that each step of the line or each each noise position gets unique. Does that make sense? So we don't want to use j, because j would be each, then we'd be adding purely random values to the segments themselves. But basically, I is saying like from the parent, we're going to use random. And then if we want, we could increase maybe the frequency for these. So they're going to be a little bit shorter. So we could just have these being like a higher frequency, if that makes sense. So the main branch is a lower frequency, but these branches here, like this main vine, is a low frequency. And then these branches, we might want them to be a little curlier or a higher frequency. But you would play around with this again to what you think you want. And if you want to control other aspects of it, you can add more iterations like this of like more line segments. And maybe with this curl noise here, we don't want it to be like the full strength. So we could reduce the amplitude of it. If you just multiply it by like 0.25, then that will be like a quarter of the strength. So I'm kind of structuring this, like all of this block of code here is going to be the branch. And then this is like the starting of the, let's just do this. Just rearrange stuff a little bit. And this will be our main vine. If you guys want to get caught up, you do another distribution of the scene. We'll keep going. So, get back into the perspective view. One of the issues here is that the children here, or the branches, they're not getting animated. They're not like, they're just appearing like on and off. So it looks a little less real. If we go back to this one, you'd see as these grow, everything is sliding around very smoothly. So that's something that definitely helps with like the organic look of this. And that's something we can go in and add. And just gonna make a global variable here. We'll just call it t for the time. I could set that to the frame if I want to, like that. And then instead of this here being frame, we can just have that be t. So I haven't really changed anything. I've just done some maintenance of my code to have a variable that represents the time or the frame. And then what we can do is make a mask for the growth distance. So just growth, say growth mask, and we can set that equal, or we can make a value for it using the fit function. So the fit function, we've used it before, but it's really useful to remap numbers to a new range. So what we want to do here is take I, or the iteration value, and remap it or fit it to a new range. We could do t for the current time, maybe time minus 10, and then t for the current time. And then the end mapping will be 1 and 0. So basically, at the current time, this will return 0, or the mask of the growth will be 0. And then when the time is like previous or from 10 frames before the current frame, it will be 1. So if we add this to our multiplier here, we'll be masking out the growth amount over time. So basically, we're smoothly scaling the growth amount over 10 previous frames to the current frame. So at the current frame, it starts at 0, and then 10 frames backward, it finally will get to 1. That is a little bit counterintuitive maybe, but hopefully that makes sense. Basically, we have to work 10 frames backwards because we can't go like forward in time of things that haven't been created yet. So basically, at the current time, it starts at 0 and then gradually expands to the full value. So that's pretty cool. We're on the right track. Another thing you might want to do is, like, right now, our vines, they might be creating too many branches, or we don't have control over it. It doesn't look too realistic. So what we can do is specify and only spawn or create a branch for certain increments. So instead of always doing this branch, what we could do is say, if and then this is, I think I've used it before, but if you use this % symbol, this is the modulo, where it just returns the remainder of a division function. So if you say I modulo 14 is equal to 0, what this is saying is every 14th iteration. So it's just saying when I can divide cleanly by 14 without giving you any remainder or any decimal amount, then this will evaluate to true. I can make a Egyptian with a curly bracket. And what I'll usually do if I'm indenting or changing blocks of code, if you just right click on this and then do edit string, or you could do Control E or Alt E, then you get this bigger code editor. And I just use this because it has the shortcuts here to tab and untab blocks of code. So for example, with this one, I want to shift all of this code over one indentation to expand or tab all of this code. So now you can see that it's working, and we're just have a bit more control over it. We do every 4th iteration, we want to spawn a curve. So this just gives you a bit more control over your vines and the extra ones, how you want them to spawn. And then changing some of these numbers around as well, you can kind of have a bit of artistic control over basically just like the shape of the vines. Whoops. So it's pretty cool. We could do another scene update, and we can keep going and add another iteration for these, another like branch off of. So with Vex, it's super powerful because you can keep kind of going deeper and deeper into things and keep adding more and more complexity or more and more detail. So even with VOPs and things like that, it would be a pretty messy kind of node tree or whatever. But I really like using Vex or just coding in general for kind of cleanly making these nested structures, nested blocks of code. So basically, we can keep repeating what we've been doing up here and make another primitive that would be, maybe we could call it leaf. So we'll say int leaf line prim. Just kind of sticking with like my current naming convention. We have the main, branch, and leaf, and then they're all lines, polylines, and they're all primitives. So that's why I've just decided to name it that, but you might as well stick with it. So we'll make our leaf line primitive. Then we want to, again, make a copy of the current position. So we need to make copies of the position so that we're not manipulating like the vine, the main position when we go in and create these branches. So this will be our leaf position. We're just storing or passing a copy of the current branch position. And then we can add the vertex. So just you copy paste, and this is going to be the leaf line primitive that we're adding the vertex to. And then we're adding a point to the vertex that's going to be the leaf position. So it still looks the same. We could just go ahead and add our next layer of nesting. So we'll do another for loop. I'll just do int k. So I'm just sticking with ijk for it's a kind of somewhat standard convention. And this one, start at 0 again. We might do k is less than 6. So I'm just thinking as you branch off, you might just want a little less length or less points for the additional layer. So this is going to be our leaf or our additional branching. And again, we can just keep doing our same process. We're going to take the leaf position, move it a little bit each iteration using curl noise. And we're going to want to use the leaf position as the main coordinate or the main source to generate our noise. We're going to want to work at a lower frequency than but maybe slightly higher than before. So basically we get even more kind of like sharp curling or detail in these leaves. And we're going to want to offset this noise using a random number based off of the parent. So in this case, the parent is j, the j loop number or j loop iteration. And it should be good. Okay, so we did it, but I forgot to add the additional points. You just do add vertex. You keep going with this. Just paste it. We have the leaves. But again, they're too long, and we might want to do some more tweaking. So in this case, let's scale this by 0.1. Whoops. I just need to do that step earlier. So we have these getting scaled by 0.1. And if we play it, we're going to want to also use the growth mask for these so that everything is cleanly or smoothly animating. And then again, this is probably a situation where we don't want to grow leaves off of every step of the branch. So we can do that using another kind of counting statement or if statement like this. And again, I'm just going to do, you could use the shortcut this time. If you do Alt-E, then you get the kind of more robust code editor. And you could just take this if statement. I'm going to put it in here, and I can start to make my comments as well. So this is going to be the leaf portion, and we're going to want to indent all of this stuff. So as you're nesting things like this, you kind of see how it makes it a little bit easier to read, or you know which statements are belonging to which loops or which kind of conditions. So, and then in this case, instead of I, we want this to be J. So we're saying every 14th iteration or step of J, but the total is 14. So maybe we'll just do every 4th. So we're getting there. I think we're just going to want to, let me just, my code is getting too long for the window. I think we're just going to want to maybe tweak some of these values a little bit to try to get maybe more interesting results. So let's maybe take the first level of curl noise and make it maybe a little bit more higher frequency, so that the swirls and stuff like that occur at a smaller scale. Then if we look at our branches, you might want to make more of them. And if we look at the leaf, depends, it's up to you, maybe we want even more of those. And maybe we want bigger, longer branches like that. And maybe we want the leaves as well to be like a little bit bushier or something like that. So there's sometimes you'll get a bit of popping or weirdness like that. That can happen if you're moving the leaves or the segments and stuff like that too far through the noises, or your noise is too high of a frequency, where it's like trying to get pushed through a noise that's running at too high of a frequency. So if we look at the leaves, move the frequency of the curl noise to a lower amount, we're starting to clean up some of that randomness. Just the jittering or whatever you want to call it. You might want to do the same with these branches, just to get less kind of like high frequency animation or whatever, because everything's parented or based off of the branch or the main vine. Any kind of like quick motions of them will like very quickly explode or generate like a lot of chaos. Let's just go back here, and maybe we want this let's just go maybe a little bit, some adjustments of the frequencies. It's kind of a balance. Like if you go too low of a frequency, you'll just get straight lines that don't curve at all. So that's kind of what I'm controlling or trying to balance with these. Maybe we want this to be a little bit smaller. Sometimes if you've looked at proportion or stuff like that, there can be some like magic numbers you might want to use. Like what is that? Thank you. Thank you, 25M42 Luck. There's the Da Vinci man. What is it? What is the name of this? The Vitruvian man. If you look at proportions for a human, like there's certain ratios or stuff like that that his limbs are taking. And generally for plants and stuff like that, there's generally like rules of proportions. So for here, you can see I'm kind of using the full amount here for the branch, and then for the vine, I might want to make that like a quarter of the length or something like that. If you don't use the right proportions or stuff like that, it just won't look as much like plants. Like you could do it if you wanted to, but it will just start to look like you'll maybe start to get lightning or other weird stuff. And you also have to be a bit careful because these iterations here, like K and J, will influence how long the branches and stuff will be as well. So if I keep doing more iterations and stuff, you can very quickly get into some really long branches or really like chaotic things happening. So we'll go back, we'd try like 24 maybe. So this might be a bit too many. And then I think this one I wanted it to be back at 16. So it's looking pretty cool. We could start to add, let me just tweak this stuff a little bit. Just getting it smoother. We'd start to add our extra branches. If we increase this point generate to maybe 12 points, then we should be getting 12 branches. But we have the same issue we were running into earlier today. This PT num isn't being used anywhere else in the code. So if we just use this and we'll add a random offset based off of PT num. So it's like we were doing for the branching. We want those to be random. So if we do that for the base vine, we offset it using the point number, then we'll get random vine positions. I'm just going to reduce the length of some of these. So as you have more like complexity, it just will very quickly look quite busy overall. So if you make the branches and leaves smaller, then it will be just look a little bit kind of cleaner. And then right now everything's just going in any direction. Like there's no gravity or there's no, with plants there's like the photosynthesis or something that derives the form a little bit. Because everything's attracted to the sun or the light. It's trying to grow upwards or that's kind of what drives the direction of stuff. So if we want to include that in our code, what we can do is when we're growing our main vines, instead of just purely walking along the curl noise or in random like noise generated like 3D directions, you can also influence a little bit of upward. So if I just do plus equals, this will keep moving or just provide an additional displacement. So you could say set, if we do 0, 0, 0, this is just nothing. But if I add I into the equation here, then you can see everything's shooting up very quickly. we might want to divide this or multiply it by a small number. Let's try 0.01. So now we have a bit of random growth motion, but everything's like constrained or generally moving in the upwards direction. If you want, you can mess around with the number of branches. Maybe we want less of them. Woo! We're getting close. The leaves, I don't know, maybe you want more, or maybe you want less leaves. Andre Flat, how's it going? This is just how we're getting the basic form. Yeah, I'm recording this for YouTube. Getting close to finishing, and then I can do another recap of what's going on. So you could also, if you have Houdini, I am distributing the file that has these code segments. So yeah, the last thing I'm going to add to get us closer to the end is, so all this stuff right now is growing at a linear rate. If we just look at this, like things are expanding and then stopping immediately. So it looks a little bit fishy, I guess. Let's go to 36 frames. So we're just looking at this portion right here. I don't know if we want to use a constant for this, do we? It's possible. Yeah, I think that might work a little bit better. Yeah, because we're kind of feeding back on the same number. That makes sense. So yeah, if you want things to be a little bit more predictable, you can just add a constant number to the upward trajectory. Thank you for that, Swash. This is a bit nicer. So everything we're looking at here is expanding and then stopping very abruptly. So if we take our growth mask and use the smooth function, let's just put this in here. So the smooth function is a little bit of a gotcha or whatever. It's just the input min and max come before the value that you want to smooth. So if we add this in, you can see now that the leaves or the growth mask, the controlled expansion of things will slow to a stop instead of before it was like an abrupt linear motion. So the smooth, we've looked at this before, but it just gives you like a S curve. It's like an ease in, ease out of your animation curve. And if we want to kind of really get interesting or fancy with this, instead of the growth mask, we can go back and use our spring equation. So we had A and W that we were using for the spring. These were kind of damping and the frequency of the spring or the oscillation. So the spring function is really nice because it gives you this organic like overshoot and settling into place. So for things like leaves that are growing, like they kind of drift around or whatever from the wind a little bit. So instead of just doing the smooth function, adding the spring function can be a little bit better. So you do we'll do negative, and then it was power. We're doing E, or you could also do like 2.7 if you're don't want to use like the logarithmic number. And then it's a negative. Of itself, and divided by A, and then that gets multiplied cosine. This is something that I kind of have written down, and if you have the previous week's file, you could use that as well. This is like a lot of these functions, you just kind of use them over and over again or whatever. So we should be good with that. And like that, something got messed up. Is it maybe I just have too many parentheses? Let's try just going to 2.7 for this. So I did this incorrectly. Okay. So we could go back to E if you want to use the actual like precise value. And now you can see when things are growing, there's like a bit of an overshoot and settling into place. So the A is damping, and the W is the spring frequency. So you do easing, or you can also do the spring that gives you a bit of like overshoot and rocking into place. Sometimes you increase this number and things will have a longer damping period of settling into place. And then if you like increase the frequency, you can see this is just getting a little bit too overpowered for our situation. You might want to maybe just do like 2 or 1 or something. Sometimes these are too low, you don't even experience like a full bounce. So it's kind of like finding a sweet spot or something like that. So just playing with those settings, and you could get something that will look a little bit natural. Looks like I'm still not seeing too much of the spring. Let's try this. Something like that might be cool. Comma? Yeah, that I think that was my mistake I had earlier, right? Yeah, I think I was just typing it. My fingers are too big for the keyboard. So we'll go back to, let's just go maybe to 96 frames. And let's just play around with this a little bit more. The spring formula, yeah, I have it. If you do go into the previous lessons, I have a node like last week's. It has there's a single node that just has that spring stuck in it. It's really nice if you're writing like procedural motion to add some extra kind of variation or organicness to things. Let's maybe make more branches. And let's try making the leaves a little bit bigger. And I think my frequency here is just a little bit too noticeable of the, so just knock it down to 3. It's just subtle enough that if you really try to see it, you can see it. But like overall, things I think just look a little bit more gentle. You can also change your growth mask if you want like maybe 30 frames of growth duration to happen. So it's not as quick of a growth expansion. Things will maybe look a little bit more natural that way as well. And then what I ended up doing in my final result was just using the polywire node. It's just a quick way of kind of skinning these or putting thicknesses to the lines in the viewport. Then just playing around with like how many curves and stuff you want. And then lastly, if you want to animate these yourself or whatever, you could change this. Instead of T, you'd do a channel frame. And then this will just be like frame number. So if you don't want like a pure just a growth tied to frame, you can create the channel, and then down here you have a slider. If you want to go into the gear, you can do edit parameter interface, and this is like your frame range, so maybe 0 to 120 for the slider. Then you can control these kind of parametrically or with a parameter. You might also want to, like right here with the curl noise, we were doing a random number from the point number. If you want to keep adding randomness to it, you can add random seed. So at this, it doesn't like it. What have I done? Did I add too much stuff in? Let's just try eliminating that. Okay, I think it was just too many brackets. So try again, add a channel. I think I know what I did. Randomness. Based off of this seed. So we add this parameter here, and now you can generate different plants or change the base curl noise frequency off of a seed. You might also just want to generate or scale this by a bigger number. Then you just have a wider range of like plants or whatever that you can grow. So this way you have a pretty nice like art directable, just an animation slider. And then if you want to make multiple copies, if you really wanted to go to town, you could like change a lot of other stuff in terms of branches, leaf length. There's a lot of other things that you might want to put into parameters. So let's just go to the frame number. If you want to keyframe this, you could do that. Like we'll start at 0, we'll end at maybe 100. And then if I do shift click, you could do it like this so that you have some easing at the end of your growth process, so that like the plant kind of slows to a stop as it gets to the top of its, as it finishes growing or whatever. So there's just a bit of extra controllability if you want. I might do less. I'm just going to add some extra keyframes to really control the easing or whatever. So yeah, hopefully you guys can see the ideas of the controllability, how much you want height to be influencing everything. and all of that kind of fancy business. And if you really want to be really fancy, like even the flowline stuff we were doing, the same idea. You could think about this. I'm just going to do less points. But the same idea, you could think about it with like a grid like this. So then you just have a ton of plants growing, make an entire jungle or some kind of fancy, I don't know, weird. It's kind of like a horror style. It's like a scary vine or something like that you're worried is going to get you or something. But yeah, it's pretty cool procedural vex effect.